So last week we talked about Nash equilibrium and dominated strategies. So this week we're going to talk about mixed strategies, which is clearly just strategies that you throw into a blender. No, it's not. Don't throw strategies to a blender. That's probably not something you can actually do because strategies are not physical objects you can throw into blenders. All right, moving on. So last week we learned about, or maybe not last week if you weren't here in class, but last week we learned about the prisoner's dilemma. And essentially with the prisoner's dilemma, we have the choices as they see in the box here. And as we determine the prisoner's dilemma, that's always better for both players to confess, which is kind of counterintuitive because -6, getting 6 years in jail, right? So these are two players and they have to decide whether they want to confess or not confess about their other person. And if they both confess, they both spend 6 years in jail. However, if they both don't confess, they spend 1 year, both spend 1 year in jail. So it's kind of like, why do people prefer this option? Well, it's not that people really prefer it. It's kind of forced by this option. And this is why it says the prisoner's dilemma. Kind of people are looking at what's best for themselves, and in the end, they get what's worse for the group as a whole, right? And also what's worse for themselves because they don't prefer this -1, -1. All right, so we learned about the prisoner's dilemma, and we learned about how confess always dominates not to confess, right? And I didn't explain this in full, but this is sort of the decision that you will never regret. So given that, so what I mean by decisions that you never regret is that you wouldn't be like, dang, I should have picked this at the end, knowing what your opponent chose. Because if your opponent chose, I don't know. Well, I should probably put the link of this presentation in chat first. So let me quickly do that. All right. That's the link to this presentation. So the decision you'll never regret because, what is it? Because you think, okay, if we're at both doing confess, then, or let's say you know that your opponent is going to do confess, like your opponent does confess, then if you do confess, then you won't regret it because not confessing will land you 10 years in jail. So you'll be like, dang, I should have chosen don't confess, except if you don't confess, you have spent 10 years in jail, so you don't regret it because you prefer spending 6 over 10, right? And if you know that the other person is not going to confess, then confessing is a decision you'll never regret, once again, because if you confess, then you'll spend only 0 years in jail instead of 1 year in jail, right?
Technically, but then they could give you like 364 days and that wouldn't be a year.
I mean, that's still worse than 0 years in jail. So you still prefer 0 years in jail though, right? Or it's still better to spend that many days than 3 full years, right? So this is sort of the decision you'll never regret. And this is sort of a way that you can define Nash equilibrium as the decision that you'll never regret. If remember from last time, Nash equilibrium is from a given position, it's when you'll never want to change. So from -6, -6, you'll never want to change. Player 2 will never want to go from not confessing to not confessing because if they do that, they spend 10 years instead of 6 and vice versa for player 1, right? And we also covered a game known as Stag Hunt, where both players got to choose between hunting stag and hunting rabbit. And then we were able to figure out, oh boy, there's 2 Nash equilibriums. So we use dominated strategies and Nash equilibriums to determine pure strategies, quote unquote, pure strategies. So what are pure strategies? What do I mean by pure strategies? Well, pure strategies are you just choose one strategy over and over and over and over again, right? Or you'd only pick that strategy. So with the prisoner's dilemma, you would only want to pick confess, right? You'd pick confess over and over and over and over again, right? That's the only thing you'd ever want to do. So that's a pure strategy because you're purely picking that one option. But sometimes you might not want to only pick one option over and over and over and over again. So we're going to see an example of this. Whoa, we're going to go over the game called Matching Pennies. So essentially, this is a pretty simple game. You and the other person are each playing a game, and each player picks either heads or tails. Now, if the things match, then you get $1 from the other person. And if they are opposite of each other, then your opponent gets $1 from you. So what would you do in this position? So if you first think about it, so if they match, you get $1 from your opponent. So that's still represented by this -1 case, right? Because you can think of these as dollars, right? The first option represents how much you get, and the other option represents how much your opponent gets, or the other person gets. Or it's probably a bad way to phrase it because sometimes you are the top player, sometimes you're the right player. So when you're on,
I'm pretty sure it's random.
well, we're going to be in there in a little bit, but just as a review from last time, this is known as a payoff matrix, and it sort of shows what you get from each of the possible outcomes of where each of the possible choices, right? So if you pick heads and the other person picks heads, then this outcome happens. What this outcome means is that the first number is how much benefit you get, or how much benefit the person on this side gets. So 1. And the second number is the benefit that the second person gets, right? So if you remember from last time, that's how it works. Which means this makes sense because, as I said before, if they are matching, so in this game, you are the player on the left side, let's just say, right? So when they are matching, you get $1 and your opponent loses $1, which is equivalent to your opponent giving you $1, right? So what would you do in this situation? Any thoughts?
I think it's random.
What do you mean by random?
Like, so if you pick heads, it could be tails or heads. If you pick tails, it could be tails or heads.
Well, if your opponent knows that you pick heads every single time, wouldn't your opponent just pick tails every single time, right? If you pick heads every single time, your opponent wouldn't pick randomly between heads and tails, right? Because they're smart and they want to abuse.
But then you learn your lesson. And then you choose the one that benefits you.
Yeah, but then they might think, let's switch my situation up because the opponent knows that they're going to switch their situation up. And then we get into this whole sort of mess of, what is it? Whole sort of mess of, oh, what does he think that I think?
Then just do random for what you do. So they don't know.
Now that is a big brain idea. Random is clearly the best option, right? Look, if you don't think about what you're doing, your opponent can't predict what you're doing, right? Clearly the best option. Clearly, right? Might think I'm using sarcasm there, but in actuality, random is the 50-50 random is the best option here, which is kind of like, why would you ever not put thought into what you're doing? So this is known as a mixed strategy because you are mixing in a whole bunch of other strategies, right? Mixed strategy means that you can pick randomly between specific strategies. So if you're picking between heads and tails, 50-50 random, that is a mixed strategy. All right. Are there any questions?
啥？
All right. Sorry, I just set this in a little time meeting, but are there any questions about mixed strategies and matching finis? So you want to pick 50-50 random, which is kind of fun, right? Clearly just don't want to think about your options. If you don't know what you're doing, then your opponent doesn't know what you're doing, so your opponent can't match. So let's look more into the logic between choosing 50-50
Unless you
random.
do it in a pattern, so then they would think you would pick heads and then you pick tails.
But you're supposed to be picking random.
If let's say that like you start picking in a pattern. If you pick in a pattern, then your opponent will realize, oh, he's picking in, or they're picking in a pattern, right? So clearly,
yeah. But after they realize that, you could just do not do the pattern anymore.
Well, that sounds like a whole mess. What if your opponent just starts picking 50-50 random after that? Right?
You pick 50-50 random?
What?
Then you pick 50-50 random?
I mean, I'd probably play 50-50 random in this situation because meh. Okay, so here's the logic to it, right? So if you pick any pure strategy, so if you pick any one thing over and over again, right? So let's say that your pure strategy is pick heads over and over again. Then your opponent is just going to pick tails over and over again and get a huge advantage over you. So if you pick tails over and over again, then your opponent will just pick heads over and over again. It kind of just looks like a no-win situation, right? If you pick heads, then your opponent wins. If you pick tails, then your opponent has an ability to win. So there are no Nash equilibriums, no dominated strategies. You can check this using the methods that we used in last class, but there are no Nash equilibriums, there are no dominated strategies, so really there's no way to solve this, right? Except we can use randomness to determine what we can do. So that means that your opponent can't predict what you're doing, because the whole point of this game is sort of to predict what your opponent is doing or what the other person is doing, right? Because if you're player 1, you always want to pick what your opponent is picking, and if you're player 2, you want to pick the opposite of what the other person is picking. So it's all about predicting what you think the other person is going to do. So if you start picking 50-50 random, then your opponent can never get better than 50-50 odds of matching you, right? They'd always be forced to get 50-50 odds, no matter what strategy they picked. Right, so even if the other person was playing, I don't know, there's no way to get any advantage off picking 50-50, right? So if you start picking 50-50,
other player like puts a security camera in your room and monitors you.
I don't know. We're gonna assume that your opponent is not breaking all privacy laws. Lots of privacy laws, and yeah. Okay, so if you pick these 50-50%, then no matter what the other person does, you'll always win with a 50-50 chance, right? Because no matter what your opponent does, there's always going to be a 50% chance that you pick the right option and a 50% chance you pick the sort of wrong option, right? Which means that your opponent can never do better than zeroing out, right? By the same logic, you can't also do better than zeroing out if your opponent just does 50-50 random, right? So if you can't do better than zeroing out and your opponent can't do better than zeroing out, then it's kind of forced that if everybody does 50-50 random, then everything goes to 0. So, woo, if you think about this, this is sort of a Nash equilibrium, because no matter what you do, so I said that Nash equilibrium means that no matter what, you wouldn't want to change your strategy, even if you know what your opponent is going to do, right? If you think about this, 50-50 random, if you know that your opponent's going to pick 50-50 random, it sort of doesn't matter what you do, right? You can pick heads, you can pick tails, but they both kind of give the same outcome. Either you have a 50% chance of winning and a 50% chance of losing. So clearly, this will give you, this is a Nash equilibrium, because you cannot change your options to do any better, and the opponent also has the same thing, right? Because this is sort of a symmetrical game. So are there any questions about this and why randomness is the best option and just not thinking about anything? Okay, so this is known as matching pennies, which is kind of fun. And oh, as the name suggests, matching pennies, you want to flip coins. So in the end, although this wasn't about flipping pennies, in the end we had to flip pennies to play this correct, or play this optimally. Okay. All right, so what if we make some slight changes to the game? So now we have slightly different payoffs, and you are playing as player 1. So instead, so your goal is still to match the pennies. So if you're playing as player 1, your goal is still to have the pennies be the same. If you pick heads and your opponent picks heads, you still take money from them. But that amount of money depends on exactly what happens.
I would probably just pick heads, because -5 is way worse than 2 or -3.
But if your opponent knows that you're going to pick heads every single time, then they're just going to pick tails every single time, right? And if that's not good, if you
so then pick random.
Yeah, but okay. Let's say that we both pick 50-50 random. So I said 50-50 random is no longer a Nash equilibrium, which means it's no longer a solution. So you're player 1, and you're going to pick 50-50 random. So what is your opponent going to do? So if you're picking 50-50 random, your opponent's going to see that. It's going to be like, huh, they're picking 50-50 random. So clearly, I get a lot more from heads than I get from tails, right? Let's say I'm player 2 because I'm the evil player 2 who's trying to take all of
So
your
then
money.
just pick heads.
So if you're player 2 and you see that your opponent is going to pick 50-50 random, you're going to see, oh, so either I have a 50% chance of, if I pick tails, I have a 50% chance of getting 3 and a 50% chance of getting -1. So that's an average of 1, right? If I pick heads, then I have a 50% chance of getting -2 and a 50% chance of getting 5. So if you add it up, that's 3. That's 1.5. So it's just always better to pick always heads then, right? You just pick heads. If your opponent is picking 50-50 random, then you always pick heads. So clearly this
So
is no
then
longer
you
a
also
Nash
pick
equilibrium.
heads.
Yeah, but didn't you say that you're picking, if you then switch to always pick heads, then they're gonna switch to always picking tails, right? Because then they're gonna start abusing that always picking heads thing. And then you kind of get into the same situation we were in last time where you're trying to outgame your opponent. So we still know that here at pure strategy, so always picking heads is still not good, right? If you're always picking, let's say you're player 1, right? If you're always picking heads, then they're always going to pick tails. So pure strategies are still not good here. So what do you do now? Our magical 50-50 random strategy did not work. Now it doesn't work. So, oh no, what do we do? Anybody have any ideas? Note how we had 50-50 here, right? Maybe things change slightly if you change those odds. Anybody have any ideas of what you do here? I mean, clearly, if you're player 1, you would prefer to pick heads over tails, right? However, your opponent knows that you're going to prefer to pick heads over tails, and they're just going to pick tails every single time. So you sort of get into that sort of bad situation. All right. Nobody has any thoughts about this? Okay, then. We're going to move on to actually showing you how to solve this game. Whoa. You might think, wow, this game has absolutely no bearing on what would happen in real life. Like, why would you ever play this sort of betting game where you're doing matching pennies and one player clearly has an advantage? But this sometimes comes up in like real world situations. Whoa. Like, let's say that you're playing in a soccer game, right? And there's a kicker and there's a goalie, and you're the kicker and the opponent and the other person is the goalie, right? And obviously the goalie is trying to prevent you from scoring goals, right? And you as a kicker can either decide to kick on the left side of the goalie or the right side of the goalie, right? And every single time between that, the goalie has a different chance of getting the ball. And the goalie can dive either left or right. I mean, in a real
Can't you just look at which direction their foot is and then know where they're going?
I mean, that's assuming.
Let's say that you're deciding
both at the same time.
Sometimes they can trick the goalie. So, if you look at real games.
Yeah, but assuming that you guys are both deciding at the same time spontaneously whether you go left or right, right? If you're like, oh boy, we're just deciding randomly between going, or not randomly, but they're just deciding at the same time between left and right. Then at first glance, and then if we have equal odds with everything, then we have the first matching pennies example, right? Because this time the goalie is trying to match the pennies or matching left and right. But let's say that the goalie has a weaker left side and then blocks goals on the left side with a lesser probability, right? Then you sort of have this sort of slight change of matching pennies, which is sort of where we get this example from, maybe in real life. All right. Does anybody still have any thoughts about what we do, or no thoughts? No ideas on what we do here.
So then the goalie would always go to the left side because you know that the left side is always weaker.
Well, then you can just always kick right, and you get around the goalie. So in this situation,
Just make sure you block the whole goal then.
this this example does have different outcomes, right? Or this example has different outcomes, but these outcomes affect the probability, right? So we see here that 50-50 random is no longer a good choice, right? I said before that previously you could just use 50-50 random to get an advantage, or not really an advantage, but get a stable state. But because of these different outcomes, if we do 50-50 random, if player 1 does 50-50 random, so the 50% chance of choosing this and 50% chance of choosing this, then we can do the math to realize player 2 gets an average of 1.5 points from choosing heads and 1 point from choosing tails. So player 2 would always pick heads. So then one must have different probabilities, right? It's not just 50-50, or else if it was 50-50, then player 2 would always pick heads and would be able to get an advantage. Okay. So with Nash equilibrium, let's go back to the definition of Nash equilibrium to try to figure out how we do this. So in Nash equilibrium, no players can change their strategies to be better off. So what does this mean? So if we think about it, let's say that your opponent is a mind reader and knows exactly what you're going to do. Right? So that means that they know so if 50-50 random doesn't work, right? Maybe we want to shake up these odds. If we shake up these odds, then maybe we can get a better result out of this. If your opponent is a mind reader and knows exactly what you're going to do, then to make sure that no players can change their strategies to do any better, right? We need to make sure that even if they were a mind reader and knew exactly what you were doing.
Your mind. If you have nothing, he has nothing to mind read, then he can't mind read. Therefore, his ability is useless.
I mean, that's not really the point of the other person being able to mind read. The point is that, let's say that they know exactly what they're going to do.
Then don't have a strategy.
The solution is not to play this game so you don't lose any money.
I mean, that's true because on average you're going to be losing, but let's say that you're trying to figure out exactly how much you lose from this game, right? Or
let's say aliens abduct you and force you to do this.
Yeah, if aliens abduct you and force you to lose this until you pay off all your life, until you pay out all of your life savings. Yep, definitely not a contrived situation. But anyways, for mathematical, for sake of mathematics, let's just assume this is a perfect world and we're actually playing this game. So with Nash equilibrium, the whole point of Nash equilibrium is that once we're at a certain point, or where each player is doing a specific strategy, then no player would want to change their strategies, right? So essentially, both players are laying their strategy out on the table, and neither of them will want to change their strategies based on the other person's strategies. So that's why you can think of this as a mind reader, or your opponent has a mind reader, right? Because you guys are both laying your strategies out and saying, look, you can't do any better by changing up your strategies based on what I'm doing. So if you think about this in probability, then you're trying to make it sure that if you choose heads of a probability of P and tails of a probability of 1 minus P, then the opponent is impartial, or the other person is impartially choosing between heads and tails. Does this make sense? This will give you Nash equilibrium. And the way that you can do this is math, which is kind of scary. But does anybody have any questions?
It's not really fair because player 2 can have $5, and you have to lose $5 if you pick tails.
I mean, it isn't fair, but let's try to see how unfair this game is if both players play perfectly and see.
So then you want to play player 2.
I mean, you probably want to play as player 2, but you want to see exactly how bad or good this is, right? Or in a perfect math world where somebody's forcing you to play these and you want to lose the least amount of money, what would you do? You want to make it so that player 2 doesn't prefer any one strategy over the other strategy, right? So then you'd have to do some math to determine this, which is kind of but all of this math, I swear it's not that bad. And all it is some basic algebra. But if you don't know algebra, it's fine. You can just like check out of this. You don't really need to understand this if you don't know algebra. I'm not going to be like, oh, I'm going to now teach algebra. But also this has relation to the algebra over Sage algebra class, hopefully. I don't know if you guys have gotten this far or if you guys have already.
We have an algebra class.
Yeah.
Like in Sage.
Yeah, so hopefully you can solve these linear equations. Anyways, so if player one has a probability of picking P of picking heads, then they must have a probability of 1 minus P picking tails. This makes sense because if they're not picking heads, then they're going to be picking tails, and the total probability has to be 1, right? Because the probability of anything happening is something must happen. So if player one has a probability of P of picking heads, then they must have a probability of 1 minus P picking tails. And then you have to do some mathematical calculations to make player two impartial, or player two doesn't care about what they pick. So for player two not to care about what they pick, then you have to make the payoffs of getting heads as the same as the payoffs of getting tails, right? So the way we can think about the payoffs of you get from heads is that if player two picks heads, then they have a P chance, or a chance of P, of getting a payoff of -2. And they have a chance of P of getting -2. They have a chance of P minus 1, or 1 minus P, of getting 5. And this is sort of the expected outcome that you get. And you see that's this equation up here. And this equation has to be equal to about what you get when you pick tails. So if we do this mathematics here, we see we have a probability of P of getting 3 and a probability of, 1 minus P of getting -1. So this is represented by this equation. And then if you multiply all of this out, my handwriting is kind of messy, which is why I just like typed it out here beforehand. You figure out that optimally, player one should pick heads with 6/11 of the time, and pick tails 5/11 of the time. Right, and if they're not picking heads 6/11, they have to be taking tails, so 5/11 of the time. So does anybody have any questions about this? So instead of playing 50-50 or exactly 50-50, now you're going to be playing, Now you're going to be playing slightly different than 50-50, but still approximately 50-50. And player two has a slightly different chance, which you can also figure out using this method. And if any of you guys are lost at any point in this, it's kind of like a lot of math. Feel free to just stop me. So this is the math for figuring out player two, and it's sort of the same thing as doing the other way around, right? So if player two has a probability of P of picking heads and 1 minus P of picking tails, the expected value that you get, player one gets from picking heads, is going to be 2 times P, and then times plus -3 times 1 minus P, and that must be equal to the expected value that you get from tails, which is this sort of mathematical thing again. Oh, that's sad. And if you do the mathematics there, I'm just going to skip over to mathematics because it's not really important. All that really matters is, wow, we can get a solution based on these values. We get that P equals 4/11, which means that player two will pick heads of probability of 4/11 and tails with a probability of 7/11.
You want to pick tails?
You're going to pick tails most of the time, but sometimes you're going to pick heads. Because if you pick tails over and over again, then player one's just going to pick heads over and over, right? So clearly that's not good.
Most of the time, just pick tails.
You pick tails exactly 7/11 of the time. You pull out your random Google random number generator, right? And if the number is 1, 2, 3, or 4, you pick heads. And if the number is anything other than 1, 2, 3, or 4, you pick tails. That's how this works. Oh boy. All right. Any questions about this? Mathematics doesn't matter too much about this. I mean, if you want to know the algebra of it, then the algebra is right on screen for you guys to look at. And if you know the algebra and want to learn about this, but overall, the lesson is that whenever we have different payoffs, we're going to get different probabilities for heads and different probabilities for tails. And not going to always have to be 50-50 if we sort of have this situation where you're always trying to outgame your opponent, like maybe in rock, paper, scissors. All right, any questions? Moving
Do
on.
we have a Kahoot today?
Oh, we will sadly not be having a Kahoot today, but what we will be having is a game theory game.
Fun game.
Yeah, a fun game at the end. So it'll actually be, hopefully it'll be pretty fun. And yeah. Okay, so let's say we want to figure out how well people actually do. Let's say that we want to figure out exactly how well people do overall. And this was really easy to do with Prisoner's Dilemma or Stag Hunt, right? Because with Prisoner's Dilemma or Stag Hunt, we knew that everybody was going to pick defect the entire time, which means that we knew that both players were going to get -10. So on average, both players are going to spend 10 years in jail because only one thing can possibly happen. You're not really averaging over anything. With Stag Hunt, you know that if they're going for the top, if they're going for the both going stag, then we know that their average is going to both be 5. If they're both going rabbit, their averages are both going to be 3, right? So we know for each of these equilibrium, on average,
if
how
it
well
was
these
a
people
food
do.
race, whoever had the most food by the end of the time or something, or
I
end
mean,
of the day, you would always pick rabbit because the other person would probably pick stag or something.
that's,
Oh, they pick.
I mean,
They could pick rabbit too.
that's true, but I mean, there's going to be something I could talk about later, which is called zero-sum games. And I'm going to just explain that really briefly about how you wouldn't always be carrying out, oh, clearly I should always pick rabbit over and over again because I'm just trying to do better than the other person's trying to do, right? So I'm going to talk a little bit later about that.
If they're trying to have stag and get 5 food, and they pick stag and you pick rabbit, you would probably get 3 ahead of them.
Yeah, but that's assuming that you're trying to get ahead of them. So all right, I'm going to talk a little about that later, but essentially with this, all you have to do is figure out the averages. So what you do to figure out how well people do on average is you take the probability of getting heads. Player 1 picks heads, player 2 picks heads, right? I don't remember the exact probability. I think this is 4 over 11.
If you pick heads, then player 1 wins that one.
This is 7 over 11.
It was $2 more.
I think this is 5 over 11, and this is 6 over 11, right? So if we do this, then we know the probability of getting heads is 5 over 11 times 6 over 11, which is 20 over 121. So then you multiply that by the payouts in this matrix. So let's say you're at player 1's perspective, so you multiply this by 2, and then you do this with this, and then so 4 over 11 times 6 over 11, which is 24 over 121, and then you multiply that by -5, and you figure out on average how well you do there, so on and so forth. And there's a lot of multiplication, there's a lot of summation, and that's kind of not important. The whole idea is that you can actually figure out how well people will do on average. And it turns out for this Smashing Pennies game, that player 1 will on average lose minus -1.182, and player 2 will on average gain 1.182. So if you're player 1 and you're looking to play this game,
so you want to be player 2.
Yeah, exactly. If you're player 1, you kind of just don't want to play this game because on average you're just going to lose money. So you want to be player 2 in this game. All right. Any questions about
What
this?
if nobody plays the game then? You guys won't earn any money.
Well, then nobody's going to play the game then because people are going to realize, wow, why would I play this game? I just lose money playing this game. But
Exactly. So you
But this
would
is
earn 0 money for doing
that's
that.
assuming that you have the option to just not play the game. But sometimes you just don't have the option to just not play the game.
So then just request for player 2.
There's some quirks to this, right? Because if you look at this, player's 1 decision only depends on exactly how much player 2 gets, right? What player 1 is concerned about is making player 2 impartial about choosing heads or tails. So player 1 only cares about player 2's payouts, right? And vice versa, player 2 only cares about what player 1 gets. It's kind of like, doesn't make that much sense, because why are we worrying about what the opponent will get when we're trying to maximize our own game? Well, in this game, it kind of makes sense that we want to minimize or care about what the opponent does, because this is something known as a zero-sum game. So if you look at this, in order to gain something, the other person has to lose something. If you think, you can think about it like that. In order to gain $2, the other person has to lose $2. If your other person gains $3, you have to lose $3, right? So this is a zero-sum game because overall, nobody is gaining anything. Like the group isn't gaining anything. Another way to think about it is that the sum of all these boxes is 0, 0, 0, 0. And also another way to think about it is that there are winners and losers, right? Because there's going to be some people who gain amounts and some people who are going to be losing. And it kind of makes sense here why you're caring about the other person, because the amount of money that your other person gains is the amount of money you are going to lose, because this is a zero-sum game. The money has to come from somewhere. So this is why we sort of care about this in zero-sum games, but this also applies to games that aren't zero-sum. So like, I don't know, Stag Hunt. This also applies to Stag Hunt, which kind of doesn't make sense, but this is just based on the definitions of Nash equilibrium. So we're at a point where no player would want to switch to strategy, because then they would make themselves worse off. Right? If you're looking at what your opponent is doing, your opponent can't really change your strategy profitably, and likewise for you. So that means that this is a Nash equilibrium. So by definition of Nash equilibrium, this is why we care about what others are doing. It's because of the definition of Nash equilibrium.
The strategy is look at what the player 2 or player 1 does.
Okay. Yeah. I also want to talk a little bit more about zero-sum games. So overall,
what's dog eat dog world?
Well, dog eat dog world means that you have to be the strongest in order to gain stuff, and everybody else is weaker, so then you take stuff from them. Because there's only a limited amount of resources in the world, so you have to fight other people for the resources. That's the idea.
Then you eat them?
I mean, it's sort of like a metaphor for everything that happens. You're taking stuff from other people, so it's like dog eat dog, everybody fight everybody. So overall, a zero-sum game can describe anything where whenever you gain something, somebody else has to lose something. However, let's think about a couple of examples. So let's think about the prisoner's dilemma. So is the prisoner's dilemma a zero-sum game? Well, clearly not, because A, not all of these boxes are zeros, right? This has -12 as a sum, this is -10 as a sum, this is -2 as a sum, right? Which means that you can do better, right? And if this game was all about doing better than your opponent, right? So let's say you're trying to do better than your opponent, right? Clearly you would always want to pick confess, right? But that's not the whole point of doing. You don't want to necessarily do better than your opponent, right? How well you do yourself, right? Because it doesn't matter how many years, if you're going to spend less years in jail than the other person is going to spend. It matters how long you're in jail, and that will cost. So does that make sense that you don't care about your own things? I mean,
the best is just not to get do not get caught doing something.
I mean, not getting arrested is pretty good, right?
Yeah.
But
So
Or don't do
brings you.
anything bad.
So overall, like in most situations, life is not a zero-sum game. You don't necessarily have to take things from other people to do better yourself. Like think about how we were like a whole bunch of years back, or thousands of years back, right? Where we had just stone tools. We are clearly doing better objectively better than all of those because we have actual houses to live under, unless you're homeless, but hopefully you're not homeless. You have a device that you're watching this that your ancestors never did have. So clearly there must be some net gain and nobody had to lose for you to get all of this stuff, right? So generally life is not a zero-sum game. All right. So moving on from this tangent on zero-sum games. Whoa. All right, so we're already quite a bit behind schedule. So I think that I'm going to skip this review video for now, but I'm going to post this on Google Classroom later. So if you want to watch this, then go to the Google Classroom later and it will be up there. Okay. So we can do this analysis to other games, right? So we can do this analysis to Prisoner's Dilemma, and we can do this analysis. We can try to see if there's a mixed strategy for Prisoner's Dilemma and a mixed strategy for Stag Hunt. So I'm going to give you guys a chance to think about. Do you guys have any prediction? Okay, that's clearly not the prediction slide, but do you guys have any predictions about what's going to happen whenever we do Prisoner's Dilemma or Stag Hunts? Like, what would be the proper mixed strategy for both of those? Or do these have mixed strategies? What would happen if we don't have mixed strategies? Anybody have any thoughts, ideas? I mean, it's definitely okay to get things wrong because it's like, I'm not even giving you ideas, so. Anybody?
You could lose a little. Well, you lose in every game.
Sure what exactly you mean by that, but in Prisoner's Dilemma, we already determined that confessing is always better, right? So in Stag Hunt, we have the stag.
Hunting rabbit is a little better.
All right. I'm going to move on to show exactly how it's happened for Prisoner's Dilemma. So if you do the math to determine exactly what you get for the probability when you confess and what happens when you don't confess, you get that the probability that you should confess is -1/3, which clearly doesn't make sense, right? You can't pick something with a negative probability. If you think about this, it makes sense that we wouldn't be able to get a mixed strategy out of this because we know that confess is always going to be the better option no matter what your opponent does, right? Which means that there's no way to randomly pick between confess and don't confess, such that your opponent doesn't care between picking confess and don't confess because your opponent always knows that no matter what you do, picking confess is always the better option.
Okay, so if you confess and they don't confess, you get 0 years?
What? Could you repeat that?
Wait, if you confess and the other partner doesn't confess, you get 0 years?
Yeah, because
yes, you
you blame it on other people.
Yeah, you blame it on the other person and you get away scot-free. But the other person also doesn't like that since
that it isn't always true though.
I mean, we're assuming that with these situations that you're going to get to be scot-free if you rat out the other person. But
yeah, but if they have evidence you both did it, then you would get like 6 years in prison or 10 years.
The whole point about this, the whole point of this situation is that they don't have enough evidence to convict you guys, which is why they're having you play this game. But if you get to go 0 years in jail, right?
To see if you're smart enough.
They're just going to want to go 6 years instead of 10 years. So they're just going to confess and you're never going to get to spend 0 years in jail because the other person doesn't like that. So in the end, we determine...
So the cops give you this because they want to know if you're smart enough to be free.
Clearly. I mean, it's not really smart. It's more of trust, or how much you trust the other person. But that was for the evolution of trust simulation. Oh boy. So we determined there was a negative probability for confess, and it sort of tells us that there's no mixed strategy that would actually work, and that makes sense because there's no way that you can make them impartial between. The whole point of this sort of equation is to make them impartial between don't confess and confess. And if confess is always going to be better no matter what you do, then there's no way that you can like change up your strategy such that they don't care about what they do because confess is always going to be better no matter what you do, right?
But like if
All right.
like if you like maybe you know what the other will do, like, and you don't trust him or her, what like you think they're actually going to lie, like about saying yes or no, what do you do?
It's still always confess, right? Because confessing is always going to be personally better for you no matter what.
Okay.
But
like I'm
probably never going to be in a situation.
I'm like, frankly, I'm like probably not going to go to jail. So
yeah. Well, this is just sort of an example, just to like explain. But you can see prisoner's dilemma in like a whole bunch of other situations, like advertising. You can see advertising as something common for prisoner's dilemma. So whenever we do this mixed strategy thing for stag hunt, where we say that P is the amount of chance that we get stag, and 1 minus P is the amount we get rabbit, do the probability, we figured out that stag hunt actually has a mixed strategy, and that is to pick stag 3/5 of the time and rabbit 2/5 of the time, because you can actually mix these up in a way such that your opponent is impartial between choosing stag and rabbit. Because at first glance, this is already, you don't know whether you're going to this is already impartial between choosing stag and rabbit because there's already a decision to choose between stag and rabbit because, you know, stag and stag, that's a Nash equilibrium, and rabbit, rabbit, that's a Nash equilibrium. So there's already a decision to choose between stag and rabbit. Rabbit, rabbit, rabbit. Okay, moving on. So stag hunt actually has a mixed strategy. So games that have pure strategy equilibrium, so that would be like stag, stag, and rabbit, rabbit, can also have mixed strategy equilibrium, which is kind of interesting. All right, so are there any questions about this?
No.
All right, I'm going to skip the rest of this because all the rest of this stuff is no fun. Also, we definitely don't have enough time for this, but because I want to get to the fun game. So essentially, in this game, so all of you guys should be paying attention because all of you guys can play right now because, yeah, you can play this right now.
I just
yeah, Ted Ed did do a video about somebody DM'd me saying Ted Ed did a video about this, and yeah, Ted Ed did do a video about this. So with that knowledge, hopefully you should be able to get a good score, right? It is about predicting human behavior. In fact, I have this linked in this slideshow, and I'm going to share that to TED Ed after class. So essentially, everybody picks a number between 1 through 100. And the person who is closest to the 2/3 the average wins. So the rules are pretty simple. So everybody in this class, everybody has to pick a number between 1 and 100, and whoever is the closest between 2/3 the average wins. But I'm going to talk about this a little bit. So I'm going to do some talking that will, oh boy, it will change your strategy in this game. So firstly, does it ever make sense to pick a number above 66? So let's say that everybody else picks 100 because lol. Then at the very highest, 2/3 the average is going to be 100 times 2/3 is going to be 66.666. So it doesn't ever make sense to go above that value, right? Because then you're just picking some number that's going to be, no matter what, it's going to be greater than the average. And okay, so I want you guys to also think about something. So a lot of you guys' probably initial reaction is, all right, so if everybody is picking a number between 1 and 100, let's say that people are randomly picking between that range. If people are randomly picking between that range, on average, people are going to say 50. So 2/3 of 50, well, that's going to be about 33, I think. That should be 33. Should be about 33, right? So for those of you who had that first initial reaction of let's pick 33 because, oh boy, we know that everybody else is going to pick on average 50. Well, if everybody else is also thinking the same thing, right? If everybody else is picking 33, then wouldn't you want to pick 22? Because if everybody else is picking 33, then 2/3 the average of everybody else picking 33 is going to be 22, right? So clearly you should be picking 22 now, right? All right. So in order to play this game,
and if everybody's picking 22,
if everybody's picking 22, you clearly pick 14, right? If everybody's picking 14, you clearly go one step further and you pick
0
further down 10. Clearly,
and then you pick 0.
I mean, you have to pick a number between 1
0's
and
the
100.
best.
So in order to play this game, I want you guys to tell me what number that you're picking by direct messaging me in Zoom chat. So just pick a number in Zoom chat.
I still don't really get the game.
So essentially with the game, everybody's going to pick a number between 1 and 100, right?
Yeah.
So if everybody picks a number between 1 and 100, then whoever guesses 2/3 the average is going to win.
You're going to say the number?
I mean, why would they give away what everybody else is picking?
I say like after.
Yeah, I will. I'm going to say who wins. All right, we're getting some nice guesses. Putting everything into my calculator right now. Oh,
What happens if you mistype? Then you have to start all over?
Oh boy, we're getting lots and lots of... Okay, I should probably expand chat actually, because this is a lot of submissions. All right, please don't submit multiple times because submitting multiple times, that wouldn't be fun. Also against the rules. All right, we see some of these numbers and those numbers. Oh boy, maybe that number and also this number. And oh, the solution to life, the universe, and everything. And we have this number and this number. All right, does anybody who wants to submit, have they submitted? Oh, we have
Yes,
that number. All right, it's time to figure out how many numbers people have actually sent me because, oh boy, this is a long list of numbers.
What are the numbers?
Well, if I gave you all the numbers, then you just be able to guess a number that was 2/3 the average. So clearly can't do that. All right, so we have this number and we have 2, 3, 4, 5, 6, 13, 7, 8 numbers, 9 numbers submitted, 10 numbers submitted, 11 numbers submitted. 12 numbers submitted, 13 numbers submitted, 14 numbers submitted, 15 numbers submitted, 16 numbers submitted.
It's gonna take so long.
17 numbers submitted. All right, now there are just 17 numbers. All right, let's see what the average is. All right, it turns out the average is 31.588, which means that 2/3 the average, which is what you guys are trying to guess, is 21.05. All right. Let's see who else, who had this closest answer to 21.05. So looking for any 21s, no 21s, no 21s. All right. Our winner is Amy Zhu, who had a guess of 22, which was the closest. Woo!
Wait, what if you guessed 21.05?
I thought I guessed a 24.
I mean, 22 is closer than 20. 22 is closer to 21.05 than 24 is, right? Well, congratulations to Amy. Woo, you are the person who won this game. Actually, we did this once in class, and
Wait, what was the number? 31 dot.
31.588 was the average. So 2/3 the average is 21.05.
Oh, that was the
Ooh.
number?
I mean, this is really a fail because only one person can win. So if only one person can win, then kind of everybody else other than that one person fails.
What if
So,
2 people chose 22?
then it would be a tie.
Yes,
Alright,
and they
that was
both win.
So in the end, the actual strategy for this game is for everybody to pick one, which kind of doesn't make sense here because clearly we didn't have somebody who didn't pick one here, right? Pun not intended. But the thing is that look at the logic from the previous thing, right? So it never makes sense to pick a number above 66 because you're never going to have an average that's above 66 unless everybody is like really stupid and picks 100 and like then if you do that, still you're still not gonna get an average above 66. So it doesn't make sense to pick a number above 66, which means that if nobody's picking above 66, then you can continue this down. So just think that nobody can pick a number above 44. Nobody picks a number above 44, then clearly it's illogical to pick a number above, I don't know, 44 times 2/3. I don't know. I don't remember. I don't know the math for that. I don't feel like doing that off the top of my head. Right, so that's kind of the logic. So that means that the only thing that makes sense for everybody to pick is for everybody to pick one. That was clearly not the winning answer because somebody picked one and did not win, right? That's because that is the Nash equilibrium. So you're trying to see how well people actually know this game. That's the whole point of this game. So there's going to be a video that you can see on the Google Classroom that I'm going to post in a little bit. But otherwise, unless you have any questions, you feel free to head out because it's already 8:03. But